Priscilla, did that mute everybody?
Okay. I don't know what just happened.
I just got cut off and I had to agree to have it shared before
Yeah, I
I
think you have
heard
to
sound
agree.
again.
They turn
Okay.
everybody off.
We might have to wait a little while till everybody catches up.
Okay. Interesting. New policy. Now that this just happened, I do remember that with external people on the call, when we start recording, people have to agree to it. That's right. I forgot that that's a new policy. So people do have to actually agree to it and then join.
We might want to find out if people are here now, because if they didn't agree.
Can folks just raise their hand if they can hear okay? Seeing a lot of raised hands. Great. Okay, well, barring any further technical difficulties, I will just go ahead and proceed. I think I was muted for the first part earlier, so I'll just start over. Hello, everyone. Thank you all for being here and for participating in the 12th year of the Drinking Water Cyanotoxin Monitoring Program. Your participation is critical in helping us assess the vulnerability and risk to cyanotoxins in drinking water across Vermont. And without your participation, we would not have such a robust program, and we'd not have all of the knowledge that we have today about microcystins in Vermont's drinking water. For those of you I haven't met, I'm Brendan O'Brien, the Emerging Contaminants Analyst with the Water Resources section within the drinking water program, and I'll be running the cyanotoxin monitoring program this year. So most of you have probably had a few emails from me thus far, and I'm sure that we'll be in communication some more going forward. I am really excited to be stewarding this program after transitioning from work primarily focused on PFAS. So this is a great addendum to the emerging contaminants issues that we face in our beautiful state. So once again, thank you all for being here. So for this training, we will start with some introductions. If everyone could please put your name in the chat, that'd be great. I guess maybe that's not necessary since I can see all of you. I can see everyone's name. There's just one caller that I can't see, but in the interest of time, I think we'll just keep it going. I wanted to segue into sort of a general introduction about cyanobacteria and cyanobacteria blooms, and then revisit what the program is, recap our results from the 2025 season, explore some trends in cyanobacteria blooms across Lake Champlain, and ultimately we'll have some talks from Ray Solomon, Scylla Larson, and myself about cyanobacteria effects on taste and odor, cyanobacteria impacts on filter performance, and then for myself, some early warning tools for cyanobacteria detection. And then we'll finish out with expectations for the 2026 season. So what are cyanobacteria? Cyanobacteria are photosynthetic bacteria. They are eukaryotes, meaning they have the, excuse me, they are not eukaryotes, but they do have the ability to photosynthesize. So essentially they use different photosynthetic pigments to make energy from the sun. And if we think back to the ecology, they are some of the oldest extant organisms on the planet. They produce energy for the entire aquatic ecosystem. Again, a fun fact about them is that since they are so old, they basically are responsible for formation of the oxygenated atmosphere that we all utilize on this planet. So we have a lot to thank them for. I know we typically think of them as a bad thing, but none of us would be here today if it weren't for cyanobacteria producing an oxygen-rich atmosphere on this planet. So just want to make that point. Cyanobacteria have several functional traits that aid in their ability to outcompete other types of phytoplankton or algae that lead to the development of harmful algal blooms. These are nitrogen fixation, colony and filament formation, and also the formation of gas vesicles that they use to provide buoyancy, which allows them to regulate their vertical position in the water column. They can float to the surface to optimize their exposure to sunlight for photosynthesis, or they can sink deeper into the water column to access nutrients. So they're very interesting organisms, and they remain in many ways unknown, specifically why they produce these cyanotoxins that we're all concerned about in terms of our drinking water. A reason that they have also been highly successful from an evolutionary perspective is that they're able to sort of uptake nutrients and store them without necessarily needing them. So they can kind of like save them for a rainy day, so to speak. They can use those excess nutrients when conditions are less than optimal to continue to maintain their growth. Another one of the functional traits that can aid in cyanobacteria success is their ability to produce these cyanotoxins. They're secondary metabolites. They aid in the cleaning of drinking water, and it's interesting that they have this deleterious effect on so many different organisms, but we really don't know why it is specifically that they produce these different toxins. What's interesting about the toxins is that they're classified by their mode of toxicity or chemical structures, but the different types of cyanobacteria that produce different cyanotoxins can be morphologically identical. So just because you have one species of cyanobacteria, it's not always going to produce that toxin. So you could have two different species that are the same, but they may or may not produce toxin. So microcystin is the toxin that we're primarily most concerned about in drinking water. It's one of the most frequently encountered of the cyanotoxins. They can cause severe liver and kidney damage. And then we also, excuse me, I'm a little behind on my clicking here. As I said, they're, sorry about that. Yeah, so anatoxins are also potent neurotoxins that attack the nervous system and can cause respiratory arrest or muscle paralysis. Then we have cylindrospermopsins, which are also capable of damaging multiple organisms or multiple organs, including the kidneys and liver. And there are saxitoxins, which are also neurotoxins that can cause paralytic shellfish poisoning if you're living by the seashore, and that's an issue. And then there's BMMA, which is a potent neurotoxin that can bioaccumulate through aquatic and terrestrial food webs. As I said earlier, another confounding factor is that a bloom may have a massive species of cyanobacteria that are known to produce toxins like microcystis or Dolichospermum, but it may not actually be actively producing those toxins. The biosynthesis of these toxins is thought to be governed by shifting abiotic factors such as light intensity, water temperature, pH, and the sudden availability of nutrients like nitrogen and phosphorus. But again, it remains poorly understood as to what the precise triggers are for producing those toxins. So we don't have clear indications of when we're likely to see toxins just because we see a cyanobacteria bloom. So that creates a real management challenge. As I said, there's no scientific consensus on the role of cyanotoxins. Scientists are still debating exactly why they make these. And because we're not sure why they're produced, it's just difficult to know when to expect them. We think that they serve the function of providing competitive advantage. They help with that excess nutrient scavenging that I mentioned earlier. And they could also help protect the organisms from further oxidative stress. Scientists also speculate that they could serve a defense mechanism, basically protecting them from grazing by other organisms, making them less desirable for algae scavenging animals. And then allelopathy, which is the biological phenomenon where an organism basically produces biochemicals that can influence the germination, growth, survival, or reproduction of other organisms to then reduce competition for resources like light, water, and nutrients. That leads us to the Cyanobacteria Monitoring Program. The Cyanobacteria Monitoring Program is a voluntary, no-cost program to analyze microcystins in surface water sources that provide intakes for drinking water systems. The program is available to all public water systems that have intakes in lakes, ponds, or reservoirs in Vermont. And it consists of weekly sampling from July through November. This week, it'll be the first full week of July following the 4th of July holiday. So that will be July 6th will be day one, and we'll go through that first week in November. It's 18 weeks. And the goal of the program is to better understand the statewide risk of cyanotoxins in drinking water sources with the overarching goal of protecting public health. Taking a look at the data from last season, 2025, we see a continuation of a trend that we've seen sort of throughout the duration of this program, which is that microcystin detections remain pretty low in public water systems in Vermont. In 2025, we saw only 2 total detections in raw water, 1 system in Lake Champlain, and at 1 system at an inland lake. These are the 2 systems, Grand Isle Fire District 4 and Derby Water System. Not calling out these systems in any way to put any shade on them, just letting everyone know kind of the geographic distribution of what we saw last year. But that said, both of these detections were in raw water. There were no detections in finished water. And comparing this to historic data, we see them primarily occurring in late summer and early fall, kind of in this window of, August to September. That's kind of when we've seen most of our detections, both last year and in the past. Last year, my predecessor, Kate Warner, gave a presentation about emergency response planning and the value to water systems for putting together a contingency for cyanobacteria in an emergency response plan. So I just wanted to check in with folks and provide an opportunity to see if any of our public water systems affected by potential cyanotoxin risk had integrated this work into an emergency response plan. So we'll just provide a few minutes. If anyone has done so, please feel free to speak up and share. Anyone at all? I am not seeing any eager response to this question, which is something that I had anticipated to some extent.
Brendan,
But
maybe I can ask a follow-up question if that's okay.
please.
So hearing no one speaking to having developed an emergency response plan, including some level of response to cyanobacteria, I'm curious if anyone would speak to sort of the barriers to doing that. You know, why, based on the presentation last year and based on the data that we're presenting you, is there a reason why either this doesn't rise to to the top of your priority, or are there any things that we can support you with in doing so? Just curious to hear if it's a resource problem or this is not, you know, a priority based on the data, anything. Anyone has any comments on that? Okay, that's okay. All right. Oh, I see in the chat. I'm new to my position, but what is a general emergency response plan consist of? Okay. That's a great question. Maybe we'll, as part of follow-up, Brendan, we can share the slides from last year, just and send them around as a sort of a repeat.
Sure, happy to.
Also another comment, unrelated, but I've got a pretty severe storm hitting here, so if I drop off, that's why. I'm right there with you, Justin. That makes a lot of sense. Yep. Yeah, Lindsay, we can definitely follow up with some information about emergency response plans from the presentation last year. Great. All right. Thanks, Brendan.
Yeah, well, with that, we transition to taste and odor in water supplies. Scylla, would you like to take over and share your screen, or can I click through slides for you?
I have made a few adjustments since I shared this last night, so let me share my screen.
Okay.
Thank you. Okay, can everyone see that? Awesome, I see some nodding. Great, thank you. Okay, I am going to give a sort of a brief presentation on taste and odor issues in water supplies associated with cyanobacteria in particular. This was prompted by Burlington Water Department last year reaching out regarding some customer complaints in the distribution system associated with taste and odor issues. And we met with Dave, I see on the call here, and talked about what are some of the common taste and odor compounds associated with cyanobacteria. And I think as part of that, it sort of, you know, we recognize that that's not something we've talked about in these cyanobacteria monitoring program trainings before. And it was a great opportunity to just, you know, take that conversation we had with Burlington last year and then bring it to the whole group, because I'm sure that despite the fact that we're not really seeing a lot of positive toxin results, as Brendan mentioned earlier, that doesn't mean that the bacteria are not there. It doesn't mean that we don't have these taste and odor compounds produced. And so understanding sort of the full picture of what cyanobacteria in drinking water can, sort of the consequences of that, not just in terms of toxins and public health risk, but also just maybe the erosion of public trust, because all of a sudden the water is tasting and smelling differently. So this is taking you through some of that science behind the taste and odor associated with cyanobacteria. Next slide. Let's see here. Okay. Why does taste and odor in drinking water matter? Why is it an important topic to be talking about? Well, first of all, the aesthetic properties of drinking water, such as taste and odor, are used by customers to assess the quality of the drinking water. So even though we all know that taste and odor doesn't reflect necessarily on the quality of water, on is it safe to drink, it is often what people refer to as their sort of their standard for do I want to drink this water or not? So it is an important topic to be considering as we are working towards, providing Vermonters water that they feel satisfied with consuming. Studies show that up to 50 to 60% of consumers who detect these earthy odors, they end up switching to bottled water, which is then increasing plastic waste and cost. And so sort of recognizing when those odors are there and how to deal with them, maybe even just communicating around them, around the use of or the existence of taste and odor compounds, so that people understand that this is not associated with a health implication. Trust lost during an event, a taste and odor event, takes a long time. It can take a year to 2 years to rebuild that trust from the consumers. This is sort of US EPA research that have shown that people will lose that trust when their water tastes and smells funky. Taste and odor compounds can pose a significant risk against that public perception and loss in trust. And really, the end result of inadequate or inappropriate communication can result in the conflation between public health risk, so the toxins being in the water, and then the taste and odor compounds being in the water. People are not understanding that there's a difference between my water smelling funky and the fact that I can still drink it and it's safe for me to drink. And that requires you all as operators, as stewards of your water systems, to communicate to the public around, wait, this is not associated with a public health risk. Let me tell you why there might, over certain periods of time, be these sort of taste and smell changes to the water and why it's okay. So that's why we're talking about taste and odor. The origin of taste and odor compounds, that is, you can group them into 4 sort of categories. But first of all, these taste and odor compounds can be detected by humans at extremely low levels. So our noses are capable of detecting odors down to 5 to 15 parts per trillion. And so it really doesn't take a lot for people to think that there's something off with their water. And when you think about those 4 groups of taste and odor compounds, you have the industrial TNO compounds. This is the hydrocarbons, MTBEs. You have the pesticides. Here we have chlorpyrifos, DDT, that can volatilize and make people detect them through their smell sensory. We have disinfection. We have chlorine, chloramines that also people can detect. And then we have all of the natural taste and odor compounds that both include inorganic. So you all know how people can detect iron, hydrogen sulfide, manganese, maybe even, they can detect that in the water. And then for this presentation here, we're focusing on the organic compounds, which include many sources, biotic sources behind these taste and odor compounds. But I will be focusing on 2 of these compounds. I'll be focusing on the 2-methyl isoborneol, the MIB, you will hear it as. And then geosmin is the other taste and odor chemical or compound that we typically associate with cyanobacteria. These 2 compounds have strong earthy and musty odors. So when people over the summertime are like, my water smells earthy or musty, it's typically associated with these 2 chemicals, geosmin and MIB. I came across this study published in 2026, so a very recent study where this group of researchers were going through a slew of studies where the compounds and their biotic sources had been identified through the study and the analysis, and basically identified 472 cases where the compound and source was identified. And this graph that you see on the slide here basically shows you, and you might have to zoom in a little bit, but it shows you here. Let me see if I can you see my pointer? Awesome. Okay. Let me just do my laser instead. So you're basically seeing here that geosmin and MIB make up the majority of the taste and odor compounds. So 65% of the taste and odor compounds in that study, including 472 cases, was due to those two compounds. And if you trace back the origin of these two compounds, you see that cyanobacteria was identified in 51% of the cases. The other major contributor to geosmin and MIB is the actinobacteria. So these are soil and water type bacteria. But primarily cyanobacteria is responsible for the geosmin and MIB taste and odor complaints that you might be getting from customers. Some of the factors affecting the production of taste and odor compounds similarly was identified and studied by this research group here, and they found correlation coefficients based on 32 studies, and basically it graphed them for MIB and for geosmin, and was able to see sort of three main environmental factors impacting the production of taste and odor compounds. And so the primary factor impacting the production is light. Higher metabolic activity and formation of taste and odor compounds occurs during the daytime when there's light. The other environmental factor that has a big impact on taste and odor compound formation is water temperature. This one they found through the studies was a little bit more complicated. There's some situations where lower temperatures may actually inhibit or activate the production. And at higher temperatures, there might be, again, some inhibition of the metabolic production of these taste and odor compounds. But in general, they saw a positive correlation between water temperature, so higher temperatures, and the taste and odor compound formation in water. Similarly with nutrients, so this is typically nitrogen and phosphorus, there is that positive correlation. More of these nutrients in the water results in higher taste and odor compound formation. I think the one thing which is interesting in terms of their graph here is also, because I know Brendan is going to talk a little bit about proxy analysis. So if you're not actually testing and analyzing for MIB and geosmin, what are some other methods out there to test for? They saw a sort of a strong positive correlation between chlorophyll A, which is the cyanobacteria and algae pigment in water. They saw a strong correlation between that for both geosmin and MIB in drinking water. If you wanted to analyze your drinking water samples for taste and odor, let's say you have you get a number of complaints across your distribution system, and you want to understand, is this associated with taste and odor compounds associated with cyanobacteria, or could it be something else? Well, then there are a number of ways to go out and have these compounds tested. There are two primary sensory analysis, and then there are the sort of instrumental analysis. In terms of the sensory analysis, you have the threshold odor number analysis, the TON. This is the one where EPA has set a secondary MCL of 3. Basically meaning if I can detect something with my nose in the water at a level above 3 TON, then you should be considering doing something about it. Advantages of this sampling methodology is it's simple, it's cost effective, but some of the disadvantages is accuracy concern. It relies on a team of lab people and their noses, which is, there can be, one of the things they mention is people's noses can get fatigued. So if you're smelling so much, you might actually stop being able to smell as well over time. So there is some accuracy concern. And the other thing is that it's really only an odorant intensity. It's not a characteristics. So you're just measuring, can I smell it? Can I not smell it? If you then want a characteristics, you can add in flavor profile analysis into that sensory analysis, which is then having, again, a team of people now trained in, besides smelling the intensity, they can also do characteristics. So is it musty? Is it earthy? Is it sweet? Is it, they can basically give a characteristics to the odor. Similarly to the TON analysis, simple, cost effective, but there are some accuracy concerns associated with this methodology. On the instrumental analysis side, we have the tool called electronic tongue, which is something you can bring with you in the field. It is rapid analysis and it's portable, which are advantages. Disadvantages is accuracy concern, again, which is always the case for these handheld devices. And then the way it works is basically a data sample is collected, you run it through these probes that are trained to simulate a human nose, and then it's running it through a data processing tool that will then, translate it into an intensity and a characteristics. And if that data processing tool doesn't have all of the compounds available, it might not spit out the accurate result. So if that's not really a tool either, then you can go all the way to, this is the gold standard, the GCMS, gas chromatography, mass spectrometry at the lab. Here you have accurate detection. It's widely used. However, it's expensive and it's time consuming. You have to send it to the lab. I did check in with Eileen with Endyne because if this is even something that they do. And she was quickly laughing. She was like, why would you test for taste and odors? You just, taste and smell, and that's it. It's apparently not something Endyne is doing a lot of. But when she looked up MIB and geosmin in her sort of database, she found that they do have method 6040D that they can sub out to a lab that they partner with out of state though, and it can detect down to 1 to 5 parts per trillion of MIB and geosmin if needed. If you don't want to test specifically for the taste and odor compounds themselves, like geosmin and MIB, alternative methods is testing for these proxies. And Brendan is going to talk a little bit more about that. But chlorophyll A, there was a strong positive correlation. You can test for that. You can test for phycocyanin and other only cyanobacteria associated pigment, color pigment. Or as we're doing as part of this study, you can do toxin analysis. But again, they're all related, but not exactly doing the same thing. This here is just an example of regulatory standards across the world, just as a frame of reference. So I said the human nose is able to detect down to 5 to 15 parts per trillion. The GCMS can detect down to 1 to 5 parts per trillion. What are some of the standards that are being applied? And really for taste and odor compounds, there's not a lot of standards out there. And typically the World Health Organization is using, the appearance, taste, and odor of drinking water should be acceptable to the consumer. And that's sort of the standard, applicable standard across International Organization for Standardization, the ISO, the European Commission, and then similarly to United States, sort of the same, but we have that 3 threshold odor number. That's a non-enforceable number. The 3 countries that do stand out in terms of regulatory standard is China, Japan, and South Korea. They actually have standards for MIB and geosmin. They need to have less than 10 parts per trillion of both of those 2 compounds in the drinking water to have it be, sent out to the customers. Okay. Key takeaways before I pass it on to Ray and Brendan. Geosmin and MIB are the dominant taste and odor compounds produced by cyanobacteria at concentrations as low as 5 parts per trillion. They are sensory proxies for presence of blooms, meaning, they are there because there's a bloom present. And when they appear, toxins may co-occur. We just don't know if it will be there, but they could co-occur. Early detection requires a tiered approach. You can go out and inspect the water. Do I see a bloom? Okay, I might see a bloom. Okay, next step is let me do a chlorophyll A sample and see, is there actually pigment associated with cyanobacteria in my water? Yes, okay, great. Well, is it at a level that is so big, so high that I should be worried about toxin production? Well, that I can have a lab confirm either as we're doing through ELISA testing or through GCMS confirmation. On the treatment side, which Ray is going to touch upon specifically for toxins, but it's associated with taste and odor compounds as well. Conventional chlorination alone is not enough to remove MIB and geosmin from water. You will need some of these specialized treatments to fully combat geosmin and MIB down below the levels of detections. And then again, as I started out, just to loop us back around to where I started, public trust is fragile, and taste and odor compounds are sort of the first thing that people will notice. Oftentimes they care about how their water smells more than whether there's arsenic in it, because they don't know about arsenic. So it's really important and for us and for you all to think about how to communicate around taste and odor compounds, about microcystin, the toxins, and just cyanobacteria in general, making it transparent and data-driven, and thinking about the communication piece as much as the treatment piece, because that is really what people will see, will smell, and taste before anything else. And with that, I'm going to pass it back to Brendan. Thank you. Maybe do we want some questions first, Brendan, or I don't know how we are doing on time.
I think we're good on time if you want to take some questions, and then it'll go to Ray.
Okay. Any questions? We are usually sharing the slides as well, and if as I mentioned, Burlington reached out last year, and so I just say, if any of you on the call have any taste and odor concerns and you want to talk it through, we're here. We're happy to talk with you and sort of brainstorm and troubleshoot with you all. So just wanted to bring the taste and odor concern to everyone's attention, as that is sort of part of the cyanobacteria conversation in general. So just if you have questions, feel free to reach out after this presentation also. Thank you.
Brendan, do you want me to just dive in here, or did you want to?
You're welcome to dive in, Ray.
I'm just going to add just a little bit to what Sela said about the taste and odor. Most of you here are operators, and even those who are not, you might want to think about doing these little tests for assessing your taste and odor. Anybody who has a system that cleans their filters with an air scour, I'm going to suggest you do this. As soon as this training is over, go up onto your scaffolding and do this little experiment. And that is, whether it's a clarifier or a filter, activate the air scour, get right in there and take a deep breath and smell what you smell. Okay? Smell it and remember what you smelled. Uh, because as I'm going to talk about a little bit more as I get into treatment effects of cyanobacteria, filtration, and a little bit on chlorination, it's all up to you, and it's all your practical experience that's going to guide you in how to treat an unusual situation. So with taste and odor, that's number one. And number two is if you don't have air scour, or even if you do, the other experiment to do is either take 100 milliliters of your raw water or your disinfected water, put it in a gallon jug that has no odor, and shake it vigorously, and then take a whiff. And remember how it smells, both the unchlorinated, if you're chlorinating, or chloraminating, if you're like CWD and using that as your disinfectant. Remember what those smell like. Share it with other people. Because if you do get a problem that you think that is a taste and odor problem, it's getting distribution, you can compare your original memory of what your water smelled like with what it's smelling like now. And maybe with a few other people, discern for yourself if you've got a problem with taste and odor. But just your own nose, as Celia pointed out, is as sensitive as almost anything that you can do from a laboratory, especially with MIB and geosmin. So that's all I'm going to say about that. Before I start, today, Thursday, there's a parade in New York City for the New York Knickerbockers. And I haven't looked at the videos, but 53 years ago, I was an avid New York Knicks fan. I was crazy for the Knicks. Why was I crazy for the Knicks? I was crazy for the Knicks, not just because I lived in the New York metropolitan area, but because of the way they played basketball. They were a team, and they overcame teams that had better players in their teamwork. And flash forward 53 years ago, 22, and add 53 to that, you get an idea of how long I've been suffering as a basketball fan until this year. And once again, that's what it took for the Knicks to win. If you watched any of those games, and you're probably not a basketball fan like I am, but it was that teamwork, it was that magic sauce that overcame, quite frankly, superior talent. And so, why do I say all this about why am I mentioning all this to you? I've got you all as a captive audience, and you are my team. All of you are my team. And what we do here, we're not recognized like the New York Knicks, and we're not worshipped like some of those basketball teams. However, as a team, the job that we do is far, far, far more important. Far more important. And I'm not going to get too much into it, but just to say that. And to go along with that, a lot of times you think of it's not a team. We're your adversaries, or we're the people you have to please, or we're the people you have to send the report to, and all this other stuff. And it's a burden for you. I understand it. I'm sort of preaching to the choir here today because you're all volunteers for this particular program. So you all have a positive attitude about it. But I just want to reinforce that team spirit that we have. And we depend on you for our ability to keep drinking water safe. You are our eyes and ears. You do what is so important, so vitally important. And so I just want to bring that out. Okay. Now, that being said, Brendan tasked me with talking about treatments, particularly filtration. And so I was kind of mulling through that and thinking, what am I going to say here? And then I asked Claude. I don't know if you know who Claude is. Claude is Anthropic's artificial intelligence agent. And I said, Claude, do me a PowerPoint, because I'm lazy, and I not only lazy, but I'm technically incompetent, and I don't do my own PowerPoints. I said, well, Claude, do something for me. And Claude put this avalanche of information in, and I whittled it down somewhat. Then I shared it the other day in person unnamed said I ought to really edit it down, which I did. And that was a very wise decision. And so in the second half of my presentation, I'm going to show you some Claude's slides and tell you what I think about them and how I agree, and some of the neat things that it has come up with, which I actually had never thought about. Okay, so treatment. What do we do if we get an outbreak, a bloom, whatever you have it? How do things change? I'm going to be really frank with you, and I'm going to tell you the answer is I do not know. I do not know. I do not have enough practical experience to tell you right now exactly how you want to deal with a big influx of cyanobacteria. But what I will tell you, what I will advise you quite strongly, is that you understand normal. You understand what is normal for your treatment. And I'm going to give you a couple little slides on what I think you ought to look at so that you can discern what is normal. And by knowing normal, you will then be comfortable in finally, once something goes wrong, being able to detail exactly what happened and why it is deviating from the norm. And if you want to call me when that happens, then you'll have a very good idea about what has changed. And I think from those sorts of things, we can better understand exactly what is going on and probably try to rectify it. So I am going to share I hope. Here we go. Whoops. Okay, well, I went to the end. Let's go to the beginning. Can you all see that?
Yes.
Okay, great. What I have put on here, and by the way, what we're looking at applies absolutely directly to rapid sand filtration plants. Anybody who is coagulating their water, flocculating, settling and filtering, maybe settling, maybe not. This graph applies to you. Now, I'm not sure if anybody here is for a slow sand filter. Uh, you know, raise your hand or
I
give me a.
I I have a Burton Island operates a slow sand filter system.
Perfect. This is not for slow sand, but I am going to be talking about slow sand right afterwards. Okay. This is a very typical plot of turbidity versus time for a rapid sand filtration plant. And I want you to think, if you are a rapid sand filtration plant, what your individual plot looks like. This plot is generic. It's not applied to any particular systems. All our systems, because of the amount of filters they have, where they have any pretreatment, what the quality of their raw water is, what their coagulants are, will be different. But this generically is a plot that you can rely on. So if you look at this plot, it's divided into three sections. Section one, the very first section, believe it or not, is the backwash, when the filter gets cleaned. Section two is where you see that big peak over on the left. That is the section where the filter comes back into service. the turbidity goes up, comes back down, and then stays sort of constant for a long period of time. And then finally at the end, whoops, what happened?
Nothing
still
happened
seeing-
on, yeah,
All
it
right,
looks
okay.
fine on our end.
Thank you. A new slide came up for me, and I have no idea why. All right. So the third section is the third section is between hours 1 and basically hour 12. You'll see a very constant turbidity of water, and then finally you see this slow rising. So let's just go through this chart and make sure that you understand it so that when you start looking at your filter run over time, you have a good idea of what your particular filter run looks like. Now, the initial period there is a backwash. And so if you picture what's going on, the water is coming from the bottom of the filter or the clarifier, or the filter in this case, and it's going up and fluidizing the bed, the filter bed, and moving all the particulate matter out of the filter, cleaning it. And so what you're seeing in the turbidimeter, which is measuring water as it comes out of the filter, is backwash water. So you're not really seeing anything of interest other than what the turbidity of the backwash water is in that first little section. But it should be there. So during a backwash, your filtered water turbidimeter ought to look something like that, a nice low number that's just reflecting what the backwash water is. Now, once the filter comes into service, you're very quickly going to see a big peak. When I say big, I mean big relative to what your filtered water quality ought to look like normally. And I've picked a number, 0.05 nephelometric turbidity units, which is pretty typical of what we see in rapid sand filtration plants. Sometimes a bit higher, all the way up to 0.1, sometimes a bit lower, all the way down to 0.02, but on average, something around that. You are not going to get 0.05 as soon as the water comes out of backwash. It's just not going to happen because the filter needs to have a conditioning period. It's got to settle back down. It's got to get rid of all of the backwash that's contaminating it. And so as new water floods into that under drain channel, the turbidity is going to rise. How high it is going to rise, I don't know. I pick 0.3, which is a pretty typical kind of number. It's going to rise very quickly up to that number. The faster you're running the water through the filter, the more quickly it's going to go up. The slower, it might take a little bit longer. It's going to rise, then it's going to peak, and then it's going to come down. Not as fast as what it rose, but over time. And I've got about 20 minutes, a half an hour before the water gets back down all the way to where it normally runs. This is what you should see in a well-run rapidly sand filter plant that's coagulating properly. You should see this peak, a very well-defined peak. And what I want you to do, if you haven't done it already, is define what that peak looks like for you. So you'd have it in your mind what you see, how high it rises, does it vary that much, how fast it comes back down, that sort of thing. Keep it in your mind and know what's happening. Now, over the course of a period of time, what is going to happen is things ought to just go perk along very, very nicely. You should see almost very little I mean, if you're at 0.05, it will go up to 0.055, maybe it'll go down to 0.045, which I haven't captured in this graph, but really it ought to be fairly constant. And so eventually when you see hour 12 and 13, can you tell me what's going on? Anybody? Somebody out there.
So
Tell me
the
what's
water is
happening.
starting to get like dirtier again, put simply.
Sure. But the question is, why is the filtered water getting dirty now? Well, filters do not run forever, do they? No. And if you picture what's going on, even a well-run plant, you picture the space between filter grains fill up with coagulated material. And so the constriction between the filter grains gets smaller and smaller and smaller. And if you're running at a constant flow rate because you have less area to push water through, what must happen to the speed of the water? The speed of the water must increase. It's almost like I'm putting 10 gallons a minute of water through a 6-inch pipe, and at hour 13, I'm putting 10 gallons a minute through a 2-inch pipe. The speed of the water is increasing. And if you think about what happens in capturing material in a filter, there's numerous forces that I won't get into that cause it to do that. And eventually the speed of the water, which is a force working against you in keeping coagulated or material through your filter, is overcome by the speed of the water. And that's especially true when the water is cold, because when the water is cold, the colder it gets, the more force it has behind it because it's viscous. And so you get this breakthrough. And so what should you be doing between hour and 12 and 13? You should be going all the way back to the beginning of this graph and starting over by backwashing your filter. This is a totally normal situation. And what you need to do is imprint this situation into your head so that if you get something bad happening, for example, a cyanobacteria bloom outbreak, you will see differences in this graph that you've got in your head. Okay, this is something that I did. By the way, this is a little depiction of, on the left, backwash water collected in the midst of a backwash. In other words, a minute or two after the backwash starts, scoop a 1-liter glass container or a clear container, any kind, into that backwash water that's going through there, and then let it sit. Let it sit. And I didn't do a real picture. I did a theoretical picture, mainly because I don't want you to think at all about what the color of this backwash water is. I made a color that looks to me pretty much like what a lot of backwash waters looks like, but not necessarily every one, because everybody has a different water and the color tint may be different. But I want you to think about doing this experiment and thinking about 2 things that should happen during this experiment. So if you see what I've got there, I've got a little arrow that says settling time. The settling time just says to me, let that beaker sit on a shelf, and if your coagulation is right and if your filtration is right, all of that stuff is going to settle to the bottom, and the top of the beaker is going to be pretty much clear, and all of that brown concentrated stuff is going to be at the bottom. Okay, so I want you to do that at any time. Just go ahead. If you haven't done it or you haven't seen me do it, go ahead and do it. Get that backwash water out of your filter when you're doing a backwash, and do it at the worst possible time, just after backwash started, when you have as much material in there as possible. Let it settle and memorize what that looks like. Or take a picture of it. Because once you know what that looks like and how fast it settles and how clear it is, if something weird happens to your water and you don't see good results like I showed you in that first graph, this second little experiment is almost undoubtedly going to confirm problems that you've got. And when I say problems that you've got, I'm talking two things basically. Number one, color. Is the color the same? Especially if it's a cyanobacteria issue. And I have seen this occasionally. If it is a cyanobacteria issue, that color tint is going to change. And usually it's going to change from what you're normally seeing to more of a greenish, bluish kind of tint to it, like you might expect as I think, Brendan, you might have alluded to, the normal color of cyanobacteria. And then it's not just color, it's what is the settling characteristics of this? If you do not see this beautiful settling step where all the flocculated material goes to the bottom and settles out, and what you see is clear up. In other words, it doesn't settle well. It stays in the whole water column. I almost guarantee you that that first graph I showed you, which shows an idealized rapid sand filter run, that's going to be messed up too, because something has gone wrong with your coagulation process. So I want to keep both of those graphs in mind to you and impress on you these two simple little things that you can do when times are normal so that we can get a handle on what goes on when things go wrong. For those of you who run slow sand plants or barrier plants, this is really not going to work for you. Slow sand plant, you do not backwash. It's a much different process, much slower. You have to, in one way, shape, or form, scrape the filter off after a period of time, months usually, so that you can get back in service. But what you can know with slow sand or a barrier approach is how fast the head loss is building up. In other words, in a slow sand plant, like say a Rutland, for example, or a Burton Island State Park, for example, over the course of weeks or months, you're going to see how quickly the filters jam up. It's not going to be a 12 or 13-hour period. At least I hope it isn't. It's going to be weeks or months, but you're going to get used to how long it jams up. And how long it jams up is going to define for you normal. In other words, Burton Island, it runs the whole summer before I have to drain it out and redo it. Okay, that's normal for you in Burton Island. And in Rutland, it might be, I don't know what your run is now, 4 months, 6 months, something like that. That's normal. And so get in your head what normal is, because especially in the case of a cyanobacteria bloom, with those kind of processes, the buildup of head loss is going to be much, 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 much quicker. Okay. Boy, how much time have I taken up? And it's a problem is I start rambling, and I can't contain myself, as you're seeing. But let's just go to what Claude has to say about cyanobacteria. And we'll go through that really quickly because, like I said before, I'm not sure exactly what you need to do if you get the bloom, but I do know that what you need to know is to recognize that something has gone wrong, and often it may be a cyanobacteria bloom. Let's see what Claude has to say about it. What they say is, as far as your filter is concerned, 3 types of clogging: physical clogging, chemical clogging, and biological clogging. And so for those 3 in the physical, you were just talking about the cells. The cells have a bridging effect, and they can quickly clog things up. Chemical fouling. This is the one really great thing I got from Claude in doing this. You'll notice this thing called extracellular polymeric substances. What the hell are they? EPS. I call it extracellular polymeric stuff. I never thought about what biological organisms excrete. Sometimes I think about biofilm. Biofilm is something that you see in distribution systems, or, if you're walking on rocks without your shoes on, you're going to the beach, you get on a big rock and you slip right off of it. What is that? That is a biofilm. Don't use the word biofilm. Use the word extracellular polymeric substances. Sounds so much better. And it explains to me really what I haven't been thinking about too much in the past. When we do get these extraordinary circumstances where all of a sudden you come into your plant one day and the coagulation scheme is totally off. I've run it for weeks, years, decades, and all of a sudden everything has gone to hell. I really do think that the key is probably this extracellular polymeric substances. And in the next slide, I tells you about that. Biological failing. This is something that's not going to be that often in a rapid sand filtration plant that's using air scour, because that's such a violent process that can usually remove that very well. But if you are a slow sand plant, or you are a plant that uses membrane, or you are a plant that is just a 1 micron cartridge filter, biological fouling to me can be a big problem, especially what Sheila was talking about before, which is taste and odor. I mean, I can see if you're getting biological fouling in your filter, an increase in taste and odor between the raw water and the water that comes out of the filter, simply because of a concentration effect in these kind, especially a slow sand plant. The EPS problem in detail. I love this. Polysaccharides, proteins, nucleic acid, highly hydrated up to 90%, make up the voluminous relative, making them voluminous relative to cell biomass. Okay, it isn't the cells. It's the EPS that causes the problem. And I think about this theoretically when you're using rapid sand filtration. You depend on charge neutralization of the particulate matter to stick it to the filter. And EPS, as in the second little thing says, EPS can reverse the surface charge of granular media and from negative to positive, altering coagulation performance and causing unexpected particulate attachment or repulsion. That says it all. That really says it all. What it tells me is this mysterious stuff, this EPS, can remarkably change your coagulation experience. So you're coming in one day, everything is great. The next day, you're calling me and you're saying, what the hell is going on? I'm saying, I don't know. But now at least I have a name where I can where I can explain it to you instead of saying to you, Jesus, I don't know. But the thing about this charge reversal, it's telling me that there's a lot of charge in this EPS that can screw up our coagulation scheme. And so then it goes to irreversible absorption, membrane fouling, DBP production. That's something I don't want to get into, but I'm sure that a lot of you are aware, especially those on Lake Champlain in 2023, especially, we had a big bump up in DBP production. Let's blame it on EPS. Why not? This is what Claude says about fouling your filters, and I don't know if any of this is true. It may be to some extent true. It may not be to some extent true, but Claude is not working with Vermont drinking water. It's working with whatever it's in its head, which is billions of data points, trillions of data points, and it's not thinking about things. All it is synthesizing the next word that it thinks it should put on the paper. And this is what it put. But you can see from what it's put there, you're going to probably get a pretty quick degradation of your filter run, which was what I was talking about before. You're instead of getting 12 hours before you start seeing breakthrough, you're getting only 5 hours, 6 hours, 4 hours, something like that. It gave me a nice slide here for optimized treatment. I don't want to get into this too much, but this is basically everything you can think about if you have a cyanotoxin problem. So this is the Toledo, Ohio model of the optimum thing you can do to cure. And when I say Toledo, Ohio, when I say that word, it's because it was the poster child of the Lake Erie outbreak of cyanotoxin. They had a very long do not drink period there. Their treatment went completely to hell on them. And so Brennan is going to be talking about this, I think, a bit later. But the thing to remember about optimum treatment for us is pre-oxidation, because this is something most of us do in one way, shape, or other. And pre-oxidation is usually for zebra mussels, or it's for taste and odor, like saying things like that. You have to, and you see the little warning sign at the bottom there, critical. Avoid pre-chlorination during active blooms. Oxidant-induced cell lysis releases intercellular toxins in the water, overwhelming downstream treatment. The main thing here is if all your toxin is inside the cell, not extracellular, and you break it apart before you filter, you have defeated the reason to filter these cells. The reason to filter the cells is to remove the majority, or at least a substantial portion of the toxin before you have to treat it downstream with chlorination or whatever else you have for processes. I'm running out of time. You guys need a break. Key takeaways. Number 3, never pre-chlorinate. Number 2, EPS is the primary fouling threat. Number 4, continuous monitoring is essential. I said continuous monitoring for just the things that you always monitor for. You need to know that, so if something's going to go wrong. I think Brenton will touch a little bit on other kinds of monitoring that might be helpful for you. Okay, that's done. I have to say two more things. And that's about chlorination. I didn't say anything about a chlorination, but these are two easy things to think about what is normal and what is not normal. Remember what is normal for chlorination. How much chlorine are you adding, and what residual do you get at the point that you measure CT? Remember that and think about it, because that should only change gradually. And if that changes quickly, probably one of two things are happening. One, you may be having some interference with this exocellular polymeric substances or something else that's eating away your chlorine, or you've got a new delivery of chlorine and the company that brought you your chlorine screwed up. Those are the two main causes. And then the other thing to do, and I'm not sure that a lot of you do this, but it's something to think about, is that you're using free chlorine to do your CT calculations. Of course, we require you to do that. But once in a while, along with that, do a total chlorine. Okay, I won't get into what combined chlorine, how it's formed, but usually in a surface water, you're going to see a difference between 0.1 and 0.3, more total than you are free. Keep that in your mind. What is the difference? It should be something in that range. If it goes up to 0.4 or higher, something different is happening there. Keep that in mind. Okay, I think I've worn out my welcome, and so I will stop.
Thanks, Ray. That was super helpful. I will say we did go a little bit long. So if folks still want to have a break, we can take 5 here. If people are feeling strong and good, we can go right on in. Why don't folks throw up a hand for those that would like to take a 5-minute break? Okay.
You can always count on Nathan.
I think Nathan can take a break and we
anyone
can keep
else?
going.
Yeah, I would say that Nathan will have an opportunity to check in with the rest of us. But without anyone else seconding that request, we'll let Nathan take his break and I can just transition into the next segment. Okay, can everyone see my screen?
Yes.
Great. So during this section of the training, I'll discuss the breadth of cyanobacteria monitoring tools that are available that could be used to help build an early warning system. I'll demonstrate how a 3-tiered monitoring framework can be applied to track different indicator variables and describe some advantages and disadvantages of specific technologies, and also provide an update on how the state is investing in new tools to gain some additional insight into early warning signs. It's important to remember that early warning tools all work by identifying deviations from an established baseline, which requires constant monitoring of these key indicator variables. If you want to know that something is going to be a problem, it's because there is a deviation from an established baseline. So I just want to reiterate that, that we can't forecast a problem without knowing what our baseline condition is. So a robust monitoring program can enable utilities, public water providers, to make proactive treatment adjustments before toxins reach consumers, as opposed to reactive management, which is a bit more costly and can be disruptive. Returning to the 2025 season summary, we see that our monitoring program has a baseline with relatively coarse resolution with some inherent bias. Weekly samples for microcystin analysis are collected on the same day of the week at approximately the same time of day throughout the season. This weekly sampling regimen does not account for environmental variables that may influence cyanobacteria blooms or the presence of toxins that pose a risk to public health. For example, it might be that by sampling raw water early in the morning, the water is cooler and cyanobacteria are less abundant than in the warmer afternoons. Or that sampling on a windy day could result in a higher concentration of microcystins as compared to a calmer day because of an increased physical breakdown or lysing of cells that then releases those toxins into the water column. Or it could be that the opposite is true, that wind promotes mixing and greater dilution of those concentrated toxins. The reality is that at this point, we don't know. And I just want to stress that I'm not trying to pick on either of the water systems shown here, but I think that we could all agree that it would be helpful to all of us if we had more information about what changes may have occurred in their source waters prior to detecting microcystin. So what is happening here in the water column? There are a variety of measures and indicators that we could use to monitor long-term and essentially create like new baselines that we can watch and keep an eye on those specific indicators to see how conditions change and then how those indicators correlate with the presence of blooms or the testing for microcystins in the raw water. So again, I'm not trying to poke holes in our data set. I just want to point out that any data set is limited by resolution bias, and we can reduce this resolution bias by increasing the frequency of observations and the diversity of indicators that we measure to improve our understanding of what constitutes a normal baseline, and therefore identify those deviations that might serve as early warnings going forward. With all that said, collecting additional water samples for microcystin analysis is expensive and time-consuming. And so for our public water systems dealing with this issue, the question becomes, what other tools exist that can provide higher resolution baseline monitoring that would help identify changes in the source water that might serve as early warning signs of elevated cyanotoxin risk? And the answer is that there are many tools available that work at different spatial scales, but many of them utilize a similar set of proxy indicators. And this is an important point. A proxy indicator is something that is a measurable parameter that we can correlate with cyanobacteria and or cyanotoxin abundance, but they're not quantitative measures of toxin concentration. That's what the collection of those samples is for, right? That's gives us that laboratory validation that we need to know yes or no, there is microcystin in the water. But perhaps there are cheaper, faster, easier methods to observe at higher frequencies that could provide more information for us about what might constitute an early warning signal. Some of these common indicators include visual inspection. This is something that you all do when you pick up your water, or when you collect your water samples. You observe the surface water. Is there a bloom that's present? Are there active signs? What's interesting about visual inspection is, although it's essentially like the simplest form of observation, it can be done at a variety of scales, using satellite imagery, at a medium scale, using UAV or drone monitoring, or simply, like I said, at the most local of scales with an operator stepping out and taking a look at the surface water. Beyond that basic visual inspection, one of the more common indicators, more common proxy indicators, I should say, are measures of pigment concentrations that are associated with photosynthetic algae or cyanobacteria. Chlorophyll A, the green in the blue-green algae, is a coarse measure that essentially provides a metric for photosynthetic activity in the water column. So it captures, if we're looking at trends, it could capture what looks like, changes in that chlorophyll A concentration could, as we're seeing that curve go up, that could be an indication that there's going to be a problem coming down the pike. But chlorophyll A is something that is produced by all photosynthetic algae and is not specific to cyanotoxins. That's where we get to the blue pigment in blue-green algae, blue-green algae, which is a pigment called phycocyanin. And cyanobacteria produce this. Not all algae produce this. There are some other organisms that produce it, so there could be some potential for interference. But for the most part, it's a pretty robust metric that's well correlated with cyanobacteria abundance. Some other indicators include adenosine triphosphate, or ATP, which is essentially a measure of total viable planktonic biomass. So it's, again, another rough metric, closer to chlorophyll A than phycocyanin. But it's something that's a fairly simple metric that's well correlated with bloom activity. And then there's general water quality parameters, like temperature, pH, turbidity, nutrients. Those are more easily monitored at a localized level. But again, tracking changes in those parameters over time can help us identify when something might be happening in our source waters. Then we get down to more direct measures of cyanobacteria abundance or cyanotoxin concentrations. And those are really only practical at a local scale because they require that we collect samples and analyze them in a lab. These include species ID and cell counts, which can be done using microscopy or molecular methods that identify toxin-producing species or genes within those species that produce toxins. And then, of course, the direct measures of the toxin concentrations themselves. But as I said earlier, the parameters that require us to collect a sample often provide the most certainty that there is likely to be some risk, but they are the most expensive and typically the most time consuming. So what I want to present in kind of the rest of this talk are some other tools. And I don't want to get too distracted by some of the large scale methods that are available, like satellite observation. We do have this tool available to us over Lake Champlain. It can be helpful because these data sets are typically long-term and they're maintained by government entities and often distributed for free. So they can be something, a data set that then is used in conjunction with these other forms of monitoring or these other variables or proxy indicators that we use to develop, a long-term forecasting model. And so looking to the future with AI and machine learning, all of these data at these various scales could be fed into a model that was developed over here, a HAB monitoring system and a forecasting model, where we're able to develop a forecast of where and when harmful algal blooms may occur, and therefore we can provide some early warnings that way. But again, pulling back a bit, this is the type of complex forecasting tool that requires skilled developers and is probably not practical for use in the context of Vermont water systems at this time. These tools, measuring general water quality parameters on site, visual inspection, and then tracking some of these pigments with some optical sensors, I think might be the most accessible tools. So that's actually what I'm going to focus on going forward. As I said, given the many types of different tools available, I think it's helpful to consider this three-tiered monitoring framework that groups tools by analytical target, relative cost, and expertise required for use, though it should be noted that there is some overlap between tiers and not all tools fit neatly into a single category, as you'll see again as we move forward. But broadly speaking, this approach is most effective when elements from all three tiers are combined. So the idea being that tier 1 consists of tools for detecting algae bloom activity, but they don't necessarily confirm the presence or absence of cyanobacteria or their associated toxins. These broad surveillance tools include basic sensory observations through visual assessment, taste and odor, and then the use of cameras or potentially UAVs or drones for remote monitoring. I mentioned chlorophyll A. I grouped it into tier 1 because, again, it's a measure of that, that algal bloom activity, but it's not going to tell you whether or not there are cyanobacteria present. So tier 1 methods are advantageous as early warning signs because they're relatively simple and inexpensive and can be therefore conducted on a routine or continuous basis. The primary disadvantage is that they can be fairly subjective and observer dependent. It sort of depends on who's reviewing the footage, whether it's, that visual inspection in person or someone piloting a drone. It depends on the observer. Tier 2 tools over here are analytical tools or potentially remote sensing options that utilize proxy indicators that can help to confirm the presence of cyanobacteria and the potential for toxin production. These include phycocyanin extraction or proxy measurement through fluorescence. There are real-time monitoring probes or in situ sensors that can also detect pigment. There are hyperspectral remote sensing with satellites, where basically the satellite monitors the reflectance of specific bands of wavelength reflecting back off of the Earth's surface. There are photonic systems, biosensors that can, detect specific compounds. And then, of course, there's microscopic enumeration, where you collect that sample and you look under a microscope and identify specific cyanobacteria species that are known to produce toxins. And then there's rapid ELISA tests, ELISA being enzyme-linked immunosorbent assays, which are essentially a way of sort of measuring types of genetic congeners, essentially, that act as a corollary for cyanotoxin production. That's something that we're looking at further within the division. So, these tier tools are sort of really best for confirming the presence of cyanobacteria. And tier 3 is sort of that final stage and the most labor intensive and expensive, and it's best utilized following detection of a bloom event in the first tier and confirmation of cyanobacteria presence in the second tier, with the goal of confirming whether or not there are toxins present. So for us, that's our quantitative ELISA. That's the samples that we send to Vail and that they measure microcystin concentration in the lab. So these methods are advantageous because they do provide confirmation that toxin-producing species are present, and that they even can provide direct measures of the specific species that are there, or the genes that are there that produce toxin, or the concentrations of toxins themselves. But given the relative low cost and training required for tier 1 and 2 tools, I think the most pressing question for all of us is which ones are best suited to use as early warning signals in the context of Vermont water systems. So this shows a tool comparison matrix where each tool is compared along the tier that they fall in, the relative speed at which they produce results that can be acted upon, the relative cost, and whether or not they actually detect those toxins, and then provides a best use case. This is sort of a adapted version of a Claude query that I put together as well, and then I've sort of cross-referenced it with a paper, an academic journal paper that is a vast summary of all the early warning tools available for detecting cyanobacteria. So again, up here at the very top is visual inspection. You get an immediate result. It's the lowest cost, but it doesn't detect toxin. It's helpful for that daily surveillance. And, if you observe something, then you can dive in a little deeper and use those additional tier 2 tools. In situ sensors, PC stands for phycocyanin, so specifically focused on, the blue pigmentation that is characteristic of cyanobacteria. You can get real-time results with those measures. It's a little bit more expensive because you have to buy an instrument, but and it doesn't detect the toxin itself. It provides a proxy indicator, but it's helpful because you can repeat those measurements rapidly and quickly over time if you observe that there's a problem underway. Satellite imagery I mentioned earlier. You can get results with satellite data. instantaneously, if you look at some of the various models that are available, but it's a very coarse resolution, right? It's not going to provide real feedback about what's happening at the intake of your water system. But from a larger scale, they're helpful. Drones and unmanned aerial vehicles, you get that same day result. They're relatively inexpensive. You get sort of that on-demand spatial bloom mapping. They don't detect toxins, but they can be really helpful for delineating the distribution of a bloom. And with a trained operator, are fairly easy to operate and deploy. There are some FAA restrictions that can, be considered sort of a disadvantage. But we're often flying over water bodies where those restrictions are less, let's say. I mentioned earlier the rapid ELISA, and then there's quantitative ELISA. There's these kind of rapid test strips versus the confirmation quantitative sampling that we do at the lab. And that's great because the relative speed, it varies whether you're using the rapid test or the quantitative lab test. The cost is moderate, comparatively speaking, and they do detect the presence of toxins. So it's a good feedback to know if you have some immediate risk. So that's kind of the gold standard for routine source water screening because of the affordability and ease of use. Then there's qPCR and other molecular methods where, as I mentioned before, you're essentially scanning the sample for genetic sequences that translate to specific known species that produce toxins or to the genes themselves that produce the toxins. So it's a bit more sophisticated. It's a bit more expensive. You get fairly rapid results, but it's not a direct measure, and I don't think is something that any public water system would ever employ. But I just am putting it up there to make you aware. Liquid chromatography, mass spec is essentially the gold standard for determining the gold standard for laboratory methods for determining, very specific concentrations. They can measure to very low concentrations. We do not have one of these instruments at our Vermont laboratory, so we don't use this, but there are many other states with greater capability in-house where that is sort of the method used for regulatory confirmation. I mentioned predictive modeling. It's helpful for forecasting, but again, it doesn't measure toxin. It can be helpful for sort of an advanced warning, but it's fairly complex, and I don't think it's a tool that anyone in Vermont is going to be using in the immediate future. So again, sort of that key take home from this slide is that we're doing everything that we should be doing within a budget, right? We're going out there into the field, we're collecting samples for analysis where we can actually measure toxins, and we're just looking and paying attention. But there's got to be some ways that we can improve. So I mentioned phycocyanin as the blue pigment that's highly correlated with cyanobacteria. So the way that we measure phycocyanin is we can do it two different ways. We can do a lab extraction and quantify the amount, or we can do a field test using a fluorometer. And fluorometers can detect, basically the way a fluorometer works is to emit light at one wavelength and shine on a piece of mass. And then the reflectance, basically what happens is that that shining of the light excites electrons within the cell. And as that extra energy then is released, it creates what's called like fluorescence. So we shine a light, we excite the ground state electron, and then the emission that it gives off is the fluorescence that we measure. And the strength of that fluorescent signal is a corollary for the concentration of pigment and therefore cyanotoxin in the water column. And the great thing about fluorometers, up here, I'll just point out, each specific pigment has its own absorbance and emission spectra. So you can target those specific pigments depending on the wavelength of light that you shine at the pigment or the pigmented cyanotoxin, or cyanobacteria, let's say, and then the wavelength of the light that is returned. So this is an example of that, the absorption and emission spectra of chlorophyll A and phycocyanin. So we've got the green over here and the blue over here. And, basically the absorption spectra, this is this area of the curve here. So you can shine a light at 430 nanometers and it's going to absorb that light. And then as it sort of, reduces its energy state, it will fluoresce along this wavelength between 662 and 669 nanometers. So that's for chlorophyll. And then phycocyanin has its own absorption spectra where the peak is here, and the fluorescence emission is measured over here. So focusing on phycocyanin as kind of a key indicator, and an affordable indicator, let's say, we at the division have decided to purchase a handheld fluorometer where we can perform routine measurements. We were approached by our friends at the Burlington City Water Department, and they are interested in utilizing this instrument over the course of this monitoring season to measure both chlorophyll A and phycocyanin multiple times daily. So as they're doing their regular rounds and checking how the plant is running, they'll be using this handheld fluorometer to monitor the fluorescence of both chlorophyll A and phycocyanin at their intake waters. And basically, you can then calculate a ratio between the chlorophyll A and the phycocyanin to determine the relative abundance of cyanobacteria in that sample. So it's a useful proxy measure. We'll see how well it works. There could be some, interferences, like other forms of organic matter in the water column. But again, hopefully, the goal here is to essentially, provide high frequency data where we can determine these relative baselines and what those readings look like, both at the baseline and then at any potential deviations, so we can estimate what might constitute a problem. And then when a microcystin detection is confirmed, we can use this tool to go out to a water system and help troubleshoot those conditions and confirm that there is, in fact, an elevated amount of phycocyanin in the raw water. So, yeah, this is one tool that we're going to be using this year. Again, with the help of our friends at Burlington City Water, we would welcome other interest, perhaps not this year, but certainly into the future, potentially this year, depending on how long Burlington wants to work with this. But yeah, it's a helpful tool. One thing I just forgot to mention was that, these instruments do require calibration using a rhodamine standard. So it's a solution that is of a similar pigmentation to chlorophyll or phycocyanin. So you basically calibrate the instrument with a stock pigment, and that's what you use to then go out into the field and measure chlorophyll A and phycocyanin. We also have access to those rapid ELISA tests. The brand that we've chosen to purchase is Abraxas. And we also have a division-owned drone and a certified pilot on our team. So we haven't really discussed widely like deploying the drone or these test strips yet, but they are tools we're considering as a way to, continue to sort of fine-tune the resolution of our monitoring program. I will mention that the Abraxas test strips that we purchased are really just good for finished water. They test down to, parts per billion. I think it's like 0 to 4 parts per billion. Ray, you can correct me if I'm wrong there, but they're not particularly well suited for raw water, which is a reason why we were interested in using them, but we haven't recommended them widely. We're looking to test them first and see what kind of feedback we get. Don't be overwhelmed by this table. This is from that paper that I mentioned, the academic peer-reviewed journal paper that summarizes.
Brendan?
Yep.
Sorry to interrupt. I just want to do a time check. We have 12 minutes left. And
Yep.
I know that you in the agenda had 25 minutes to wrap up with the cyanotoxin season. So just want to make sure that we make sure to wrap it up for people to head out at 3 o'clock.
Yeah, let me just get through this. Thanks, Zilla.
Yeah, no problem.
So I just wanted to point out basically, again, what we're doing is that tier 1 visual inspection, and then we have our tier 3 confirmation using the ELISA test. I thought this would be helpful for reference, so I included it. It's a bit redundant, but if we're distributing the slides, I thought it might be helpful. And then looking to the future, if we're equipped with this handheld fluorometer, we can measure both phycocyanin fluorescence and chlorophyll A fluorescence, both of which are, let's say, moderately to strongly well correlated with cyanobacteria. So it's a great tool for this purpose, and hopefully will help us get greater information about what constitutes a change in the water column that would warrant an early warning. So again, this is just sort of a reiteration of that last table, showing what we're sort of doing here with all of you in Vermont with our monitoring program. So in summary, no single tool can do it all. Effective early warning requires a layered, tiered monitoring approach. In situ phycocyanin sensors can offer one of the best continuous real-time detection tools. Satellite and drone tools excel at spatial surveillance, but cannot detect subsurface blooms. That's something I didn't mention, but is something worth keeping in mind. ELISA is the practical workhorse for routine toxin screening, while LCMS is the gold standard. qPCR provides genetic early warning, but the gene presence alone doesn't necessarily confirm toxin production. Predictive models can deliver an advanced warning, and basically require historical data sets to calibrate. And then getting back to where we started, a written HAB response plan with defined action thresholds should be an essential component for every surface water system. So without skipping a beat, I'll just head right into the 2026 season and what we're expecting. As I said earlier, the season will run for 18 weeks from July 6th through November 6th. There are no significant changes to the practice or sampling protocol. There are some minor changes to the courier routes. They really just affect our partners in the Lakes and Ponds program, so it's not something that anyone here has to worry about. Basically, all of your drop sites are the same as last year. And we are only sampling for microcystin. And then there are these state holidays. I'm going to send all this information out to all of the operators who are participating directly, but I will mention it. There are 2 Monday holidays. Typically, our Lake Champlain systems collect on Mondays, and the samples are stewarded off to Vail by courier service. But there is the Labor Day holiday on September 7th, and so pickup and collection will move, or collection and pickup will move to the 8th on Tuesday, the following day, and then Indigenous Peoples Day on October 12th will also move to Tuesday. For reference, I'll send out the cyanobacteria monitoring practice for you all, but generally the program runs as follows. Participating water systems sample from July 6th through November 6th. Following sample collection, they get dropped off for couriers to pick up and take to the lab at designated drop sites. Vail will analyze raw water for microcystins on Wednesdays, and in the event of a detection, we'll analyze the finished water samples as soon as they can. So if a raw or finished water has microcystins that are like above the health advisory threshold, they'll also include a confirmation sample. If the confirmation sample for finished water exceeds the health advisory, the system will issue a do not drink notice. And again, if the raw water is above 0.3 milligrams per liter, again, that health advisory, we will use a calculator to assess finished water risk and determine additional sampling frequency, which is detailed right here. So in each of your kits, just like last year, we at the division have packed the kits, and our friends at Vermont Rural Water Association will be distributing them. In each kit, there are 2 amber glass vials. One of those vials contains sodium thiosulfate, which is a preservative to quench the chlorine that could be present in finished water. So these are the finished water samples, the ones that have sodium thiosulfate inside. The ones without a label mentioning that they have sodium thiosulfate will just be plain amber glass bottles. So you'll have 2 bottles, one for finished water, one for raw water, 2 sample labels that are not attached to the vials. I think it's best practice to fill those out on a flat surface and then apply them rather than trying to write on the bottle. We'll talk about messy labels in a moment, but the lab really prefers that labels are clear and easy to read. I've given you all a Sharpie in those kits for writing on labels. And then each kit will also contain a field sheet shown here that's contained within a small Ziploc bag and can be returned to that Ziploc bag after it's been filled out, so that it's protected and doesn't get wet from any residual moisture in the sample bags. So collecting water samples. Be sure to identify what the source of the water is prior to sampling. My recommendation is that you collect all of your finished water samples first, or your one finished water sample first, I should say, whenever possible, to prevent possible raw water contamination. Just think of it like this. The raw water is likely to have a higher concentration of microcystin than the finished. So if you're getting your hands dirty, it's just sort of a good sampling practice to sort of sample the cleanest form of water first before the dirtiest. So finished to raw is the preferred whenever possible. Sorry about the order here. Use the provided Sharpie or a ballpoint pen to write collection information on the provided label, and please allow that ink to dry prior to applying it so that it doesn't smudge. Uncap the bottle and fill to the shoulder. This is what we consider the fill line. Again, these instructions are provided on the sample field sheet. Replace the cap, dry the outside of the bottle. Once the bottle is dry, that's the best time to adhere the label because it's had some time to dry and hopefully won't smudge. Complete your sample field sheet. Repeat steps 1 through 5 for the raw water sample after you've collected your finished water sample. And then you can put that field sheet inside the small plastic bag that it was originally in, seal it up nicely, put it into the large sample bag with both of your raw and finished water samples, and then place them in the cooler on ice. For the labels and field sheet, as I said, please, best practice is to collect the finished water first whenever possible. We've just been getting a lot of feedback from the lab that some samples have come in with illegible writing or it's smudged. So I just gave some pro tips here for what I consider best practice, which is to write labels on a flat surface prior to application, make sure that the ink dries, and And I want to mention, I gave you all Sharpies, but they do smudge. So if you have a ballpoint pen, that works really well too. But please no ink pens, because they always smudge on these labels. If a label does become ineligible, substitute another one. If you need extra labels, because that keeps happening, reach out to me or the folks at Vermont Rural Water, and we can get you some additional labels before the end of the season. You could always use a piece of tape as well. Just make sure that all of the information is there. We're using military time. That's a request from the lab this year. Helps that you don't have to write AM, PM, but if military time confuses you, then feel free to write it. It's just about trying to reduce any confusion at the lab. So they prefer the military time, but if you write AM or PM, that's helpful too. Make sure you write your full name. That's also really helpful for the lab. Oops, just went backwards. And then just make sure that you check your intake area to confirm the presence absence for a bloom. I think some folks were forgetful of that last year. So sample drop off. Once again, the Lake Champlain systems are on Tuesdays. Inland Lake systems are on Mondays. Please, 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 please drop your samples off at least 30 minutes prior to the designated pickup time. And let me know ahead of time if you won't be able to collect a sample that week so the courier can skip that stop. I'm just going to skip through here. I already mentioned the holiday changes. I'm going to send all this information to you all specifically with some additional details about the drop site, like where the cooler might be located. So if it's your first time, it's not difficult to find, and you have a little bit more information than just the basic address. So accessing the results. Once we receive the results from Vail, we expect to get them on the Friday following sampling. And if the samples have detections, I will notify all of you directly. You'll be getting an email or probably a call or both from me. And then they will be uploaded to the Drinking Water Division website by the Monday following test results. I will also include all of the folks at the health department and others across the state who are involved with this program to let them know as well. And then those results can be accessed here at this URL, and they'll be consolidated into one link where you can see basically the results across the full course of the season. So wrapping up quickly, just in time, future directions, where do we go from here? Like I said, we've got 11 years of data now with relatively few detections. So what other tools can we implement to reduce some of our, our systemic sampling bias and better understand some of the variability of cyanotoxin blooms and toxin risk? And this is a bigger question that I'd love you to all take home and think about. And feel free to email me your thoughts at any time. But should we develop this into a regulatory program? Would it help to build public trust if there is a specific regulatory program that looks at cyanotoxins and the relative risk? So I'd be really curious to get all of your feedback on that. I think we're kind of out of time today, but I welcome your input on that topic at any time if you choose to send that along. Thank you. 301.
Thank you so much, Brendan. That was great. Yeah, so it's 3:01. I'm happy to stay on for another couple of minutes if someone has a question and they want to, share it right now. But I also recognize that the training is over, so people are free to drop off as they need to. So thank you so much to everyone for joining today. And we look forward to another great cyanobacteria monitoring season. And if you have any questions, you know where to find us.
I'll stay on for any questions as well, should they come up.
Thank you all for your time.
You're welcome. Thanks for joining, Justin.
Brendan, you spelled my name wrong.
Yeah.
That's okay. They emailed me though.
Sorry, Ray.
You
I'm
got
gonna
it right
blame
over on the
Kate for
left.
that one. I didn't catch it.
That's okay.
All right, I'm gonna go ahead and stop the recording. I don't think that there's any questions coming our way right now, so